Dear students, welcome to yet another online tutorial on principles of communication system. So we have been discussing about noise performance of continuous wave modulation systems, right? And we have seen the noise performance of DSBSC, and further we have seen noise performance of standard AM using envelope detector. And in last class, we have derived the figure of merit or noise performance of FM system, which uses a frequency discriminator for demodulating the signal. Right. And we have seen this to be equal to 3kf square p by w. This is what we have done in past two classes. Actually, we have from the basics we started and we derived this figure of merit. This figure of merit is nothing but SNR at the output divided by channel SNR. Right. So we found it to be equal to 3kf square p by w square. I'll just remind this kf is nothing but what frequency sensitivity. P will be average power of the message signal, and W, which will be approximately equal to maximum frequency content of message, and this is the cutoff frequency of the low pass filter, which is used at the output end of the demodulator. So this is what we have seen. So in this class, what we'll do is we'll just solve an example, right? Or we'll take it as I'll take it as a general case, right? And we'll solve it like a derivation, but you can expect specific numerical problems also from this, right? So what we'll do is we'll try and find the figure of merit of a single tone FM modulation system with a sinusoidal wave of frequency FM as modulating signal, and peak frequency deviation is delta F, right? So what we need to do is we need to find figure of merit. So we already have the expression to find equation to find figure of merit. It is 3kf square p by w square, right? So this w it is approximately equal to fm. So now what are given us? Given the message frequency is fm, that is given, and frequency deviation is delta f, that is also given. So let's see how we can proceed further and solve this problem. So please keep in mind. So what we need to do is finally we need to find, right, figure of merit of this single tone FM signal, that is equal to 3 kf square p divided by w square. So given, right, it is given w is equal to fm. It is already given. We don't know what is kf. We don't know what is p. So we need to find it out. Right. For that, what we have is, right, so as it is, maybe we'll start by writing the standard time domain expression of single tone AM, right? So the standard time domain expression of single tone AM will be AC cos 2 pi FCT plus 2 pi KF integral 0 to T m of tau d tau, right? So here m of tau as such is not given. What is given is message frequency is given, right? So and it's a single tone modulation system. This is a general expression for FM, general time domain expression for time domain expression of general FM signal. So now maybe what we can do is we'll try and write the what if it is a single tone modulation system, how it will change, right? So we have already seen this. S of t will be AC cos 2 pi FCT plus beta sine 2 pi fm t. So if it is a single tone modulation system, right? So the standard time domain expression reduces to AC cos 2 pi FCT plus beta sine 2 pi fmt, and this beta is nothing but we know it is delta f by fm, where delta f is frequency deviation, and fm is the maximum frequency content in message signal, maximum frequency content of m of t, right? So in this case we have assumed m of t to be equal to some am cos 2 pi fmt, right? And this delta f is nothing but what? Delta f is nothing but kf into am. So but most of the information we can see it's missing, right, in this problem. So what we can do is, right, we can, whatever delta f and fm are given, right, delta f and fm are given, so we can find beta, right. So if we compare these two, right, if we compare these two expressions, the standard expression and the one which is specialized for singleton, right, we'll try and compare that and let us see whether we can get some useful information, right. So that's what we are going to do next, right. So uh, what we can write it as s of t is equal to ac cos 2 pi fct plus delta f by fm sine 2 pi fmt, right. So now we, if we compare the standard expression and the expression for single tone fms, that is, if I call it equation number 1 and if I call it equation number 2, if we compare equation number 1 and 2, right, we will get 2 pi kf into integral 0 to t m of tau d tau is equal to delta f by fm sine 2 pi fmt, right. So which means, right, so from this maybe we can find what is m of t, right. M of t as such is not given, right. If you solve this is actually what right, an integral equation, right. If you differentiate on both sides, mostly we'll get actually what m of t, right. So from this we can find, so we have integral 0 to t m of tau d tau is equal to 1 by 2 pi kf times delta f by fm sine 2 pi fm t, right. So now if we differentiate, so on left hand side I have actually what integral 0 to t m of tau d tau. So you know, if you differentiate with respect to time, you will get m of t, right. And so we can differentiate on both sides with respect to time, right. Differentiating on both sides with respect to time, so differentiating both sides with respect to time. So what we have is d by dt of integral 0 to t m of tau d tau is equal to 1 by 2 pi af times delta f by fm times d by dt of sine 2 pi fmt, right. So this left hand side will become m of t, this right hand side 1 by 2 pi kf delta f by fm, d by dt of sine 2 pi fmt will be cos 2 pi fmt, right. So I will write it 2 pi kf. So taking it as a general example and solving from this, you can get like specific numericals. You may be asked to find only what is m of t, or you may be asked to find what is output snr, all those aspects. But as I'm taking it as a general example and solving, right, I'll show the detailed steps. So delta f by fm, so this will be equal to, sorry, sorry, delta f by fm, this is cos 2 pi fmt into d by dt of 2 pi fmt, right. So that will be 2 pi fm, so that 2 pi and 2 pi will get cancelled, fm and fm will get cancelled, right. So here you can see, okay, I'll write 1 by 2 pi kf delta f by fm cos 2 pi fmt cos 2 pi fmt into 2 pi fm. So now we can see this fm and fm will get cancelled, 2 pi and 2 pi will get cancelled. So what we have is delta f by kf, right. So delta f by kf cos 2 pi fmt. So that is our message signal, right. So this is equal to m of t is delta f by kf cos 2 pi FM T. So we know this is a now we got what is a message signal, right? We got what is a message signal, that is delta F by KF cos 2 pi FMT. So the message amplitude is delta F by KF. So that can be a question. So these details may be given. They may ask you to find what is the message amplitude, right? So then delta F by uh, right, KF is message amplitude, right? So now further, so what will be power, message power? Now we need to find what is P, right? P, that is message power, average power in m of t, that is equal to, right? So this is our magnitude part, and it's a cosinusoid. So it will be, if it is am cos 2 pi fmt, average power delivered to a 1 ohm resistor will be am square by 2, right? So instead of am, what we have is delta f by kf. So what we have here is delta f square divided by 2 kf square. So this will be our power. Message power will be delta f square by 2 kf square. So now, as we have this, we'll try and substitute this, right, in the expression for figure of merit. Right. So this figure of merit, it is the expression for figure of merit. We already know it is equal to 3 kf square p. Still, we don't know what is kf, but if we substitute the substitute for p in this expression, this kf will get cancelled, right? So that's why even if kf is not given, right, we can manage without kf in this. 3 kf square p divided by w. So it will be 3 kf square. Instead of p, you can write delta f square divided by 2 kf square, and instead of w, you can write fm, right? So what happens is this kf square and kf square gets cancelled. So we get the expression for figure of merit as, uh, 3 times delta f square divided by say the 3 times delta f square divided by 2 fm. So we are getting the value of this as 3 times delta f square divided by uh, 2 fm. So that is the figure of merit. So now delta f is given, fm is given, so you can easily find what is the say the figure of merit. So it should be w square. I'm really sorry. It should be w square. So it should be fm square. So that is 2 fm square, right? So 3 times delta f square divided by fm square. So but you know this delta f by fm, right? It is the uh, modulation index, right, of fm, right? So but delta f by fm, it is actually what equal to beta, that is the modulation index. So in general cases, instead of modulation index, what we'll do is we'll call it actually what frequency deviation ratio, right? If it is not specifically a single tone modulation, but we know the maximum frequency deviation is this much and maximum frequency content in message is fm. So then the ratio of maximum frequency deviation to maximum frequency content, we'll call it actually what, we'll denote it as d, and we can call it as actually what, frequency deviation ratio, right? So maybe you can tell beta or modulation index is actually what, the frequency deviation ratio in the case of a single tone fm, right? So now delta f by fm is beta, right? So what we can do now is we can write it in terms of beta. So figure of merit in this case is equal to 3 by 2. Then delta f by fm is beta. So delta f by fm, the whole square will be beta square. So it will be 3 by 2 beta square. This will be equal to what, 3 by 2 beta square, right? So this is our final result. So this is equal to 3 by 2 beta square 3 by 2. That if delta f, if they have given numerical values for delta f and fm, easily we can find what is the figure of merit. Now, what we can do is from the specific example, we can like obtain some more results, right? So maybe we have studied in single tone, right, or in general single tone FM, right? We can categorize it into what narrow band FM and wide band FM. So this narrow band FM is the case when beta is much less compared to 1, and wideband FM is actually what beta is comparable to 1 or beta greater than 1. So but we didn't uh, say we didn't have like no like what actually is the strict bifurcation between narrowband FM and wideband FM, and we have even seen, right, this is similar to what AM, right? This is similar to what AM. It will have only a carrier, an upper sideband and lower sideband, right? The bandwidth is equal to what 2W in narrowband FM, but in wideband FM, we had actually what Carson's rule to find the bandwidth, right? So it was two delta F into 1 plus 1 by beta, right? So we have seen this. So this narrowband FM, it is almost similar to what AM. Narrowband FM was similar to AM, right? So for right, so maybe figure of merit of this NBFM, right? Figure of merit of NBFM will be same as that of right AM. So the approximation FOM of narrowband FM will be same as that of right AM. So maybe we can consider the case when modulation index equal to 1, right? Our modulation factor is 100%, right? In that case, if you remember, the figure of merit was equal to 1 by 3, right? The figure of merit was equal to 1 by 3. The modulation index equal to 1 was the case where we had maximum power efficiency, right? The power efficiency was 33.33 percentage, and the figure of merit we found in previous classes, it is equal to 1 by 3, right? So now maybe we can use this result to find out the value of beta, right? Maybe an approximate value of beta below which we can call a single tone FM as narrowband FM, and above which we can call a single tone FM as wideband FM. So that is what we are going to do now. So this for a narrowband FM, right, it will be 1 by 3, right? It will be 1 by 3 or less. Figure of merit will be 1 by 3 or less, right? So a narrowband FM with maximum power efficiency can have a figure of merit equal to 1 by 3, right, or even less, right, if power efficiency, if we are ready to compromise. So now the limiting case is this 3 by 2 beta square is equal to 1 by 3, when for which value of beta we can find out 3 by 2 beta square is equal to 1 by 3, right? Or if a modulation system has to be wideband FM, right? This why we are particular about wideband FM? This FM has a very beautiful property, right? If we are ready to spend more bandwidth, right? If we are ready to what spend bandwidth, if we are ready to use more and more frequency range, then what we can do is we can have better noise performance, right? So we always want to like go for WBFM with actually what a better noise performance, which means we should have actually what more bandwidth. So in that case, for a singleton modulation to be equal to WBFM, 3 by 2 beta square should be greater than or equal to actually what 1 by 3, or the limiting case is 3 by 2 beta square is equal to 1 by 3, right? Or maybe I can write, so for wideband FM, right, 3 by 2 beta square is greater than 1 by 3. So I can write now maybe beta should be greater than, say, beta will be should be greater than or equal to root 2 by 3. That is equal to actually what 0.471, right? Beta should be greater than 0.471 for wideband FM, right? And it should be less than 0.471. So as a maybe we can consider actually what the boundary or the border value of beta, right? If beta is greater than 0.5, we can call it as actually what? Wideband FM. And if beta is less than zero point 0.5, we can call it actually what? Narrowband FM, right? So this is the transition region between beta equal to zero point 0.5 is the transition region between wideband FM and narrowband FM. So now one more possible question is they may give these details, right? And they may ask you to find whether this given system is a um, wideband FM signal or narrowband FM signal. In that case, what you should do is you should evaluate the value of beta. It's nothing but what delta F by FM. If it is greater than zero point 0.5, it's for sure it's right wideband FM. If it is less than zero point 0.5, it is actually what narrowband FM. So this is the um, one a typical example. From this you may get actually what different problems, right? Different problems you may get, even though we have done it as a general case. I didn't like assign any what numerical values to delta F or FM, but right, if numerical values are given, and you should be able to what solve it. Why? Because it's quite straightforward. So in this session, I think we'll have right. We'll wind up with this particular problem. So in the next live sessions, what we'll do is we'll discuss about the capture effect and FM thresholding effect, pre-emphasis, de-emphasis, all those aspects, and we'll wind up the this module and we'll move on to the fourth module. Right. So thank you.